When a lightning bolt strikes, the atmosphere is violently balancing a massive electrical ledger. Millions of volts of potential energy snap across the air, instantly equalizing a buildup of tension. Ancient observers watched these same mechanics on a much smaller scale. By rubbing a piece of amber with fur, they could create enough attraction to lift light objects like hair or straw, observing the same physical rules as a thunderstorm, but contained in a single room. Benjamin Franklin used apparatus like these to turn observations into rigorous philosophy. He proposed a one-fluid theory, permeating all matter, to establish a binary system. An excess was labeled positive and a deficit negative, noting opposite states attract while identical states repel. These binary rules of attraction and repulsion operate at an immense scale, governing the massive industrial halls and generators that power modern civilization. Eventually, we discovered that charge is not a continuous fluid, but is instead carried by discrete subatomic players. Protons carry a fixed positive value, while electrons carry an exactly equal but opposite negative value. But identifying which particles carry charge only describes the mechanics of the game. It leaves an ontological void regarding what this property actually is, and why these specific particles are required to carry it. To understand the true nature of charge, we must look to quantum electrodynamics, or QED, which replaces classical fluids with interacting fields. In this framework, charge is a coupling constant. It's the mathematical node where an electron field intersects an electromagnetic field. This constant measures how strongly a particle interacts with a photon, dictating the probability it emits or absorbs energy. At the quantum level, charge is no longer a physical load a particle carries. It is the specific interaction strength that defines a particle's relationship with its environment. While electromagnetism relies on a binary positive-negative game, the strong nuclear force requires much more complex mechanics to hold an atomic nucleus together. Quarks operate under a ternary system called color charge, utilizing three distinct values: red, green, and blue. By exchanging particles called gluons, these color charges enforce a rule known as confinement, preventing quarks from ever being found in isolation. Despite different rule sets, both electromagnetic and strong forces are subject to the conservation of charge. In any isolated system, charge cannot be created, it cannot be destroyed. Whether an industrial generator or a subatomic collision, it's a perfect zero-sum transaction. This suggests the universe is governed by an unbreakable internal audit. To understand why, we must find the code enforcing this total conservation. In 1918, a mathematician named Emmy Noether uncovered a link between the conservation laws of physics and the mathematical geometry of the universe. Noether's theorem proved that every conserved quantity in nature is the direct result of a continuous symmetry in the laws of physics. The conservation of electric charge is a consequence of U1 gauge symmetry. This means that the physical laws of a system remain invariant even if we perform a localized phase shift on the quantum fields. Charge acts as the mathematical generator that allows this specific symmetry to exist within the fabric of reality. Modern theoretical work like Kaluza-Klein theory attempts to take this abstract symmetry and find its physical origin in the structure of space itself. This theory proposes that electric charge is actually a particle's momentum as it moves through a curled-up microscopic fifth dimension. A lightning strike, or a static shock, is a physical manifestation of these internal geometric requirements enforcing a balance across dimensions. Electric charge is the evidence that our universe is built on a foundation of unbreakable